Welcome back to Computational Thinking for Modeling and Simulation. I'm Dan Fry, and we continue our module on integration. I want to show you an example so that you can see how numerical integration techniques like rectangle rule can be used in a real-world scenario. So we're going to talk about a robot seeking to find its way and navigate and determine its position over time using integration. Now, in our labs, a researcher placed optical encoders on the wheels of a robot. So this figure here gives you an indication of what a robot wheel might look like. We pasted on a disc that had light and dark bands on it, and we fixed to the chassis two sensors A and B that returned signals: high voltages when there was a reflective or white surface in front of them, and low signals when a non-reflective or black surface were before them. And you can probably appreciate that a device like this, just one sensor, could give you an indication of the speed of the wheel, and that would give you incremental encoding of the position of the wheel, but that you would not be able to differentiate with just one sensor alone whether the wheel was turning forward or reverse, because switching back and forth between high and low signals would be observed in either forward or reverse rotation. But by including this second sensor that is what we call out of phase by 90 degrees, helps to disambiguate the two signals, because you'll see the patterns are different in forward and reverse. And we'll come back to this example of computational thinking in another section, because we need differentiation to be able to deal with that. But for now, let's say that I've done that processing already for you, and we can get velocity from our encoders and determine the sign of that velocity. Now, these encoders provide you a data file that have the counts of the increments of advance to left and right, and I've processed those already to give you the velocities forward and back. And our goal is to accomplish something called dead reckoning. When pilots are flying, they use that process called dead reckoning to take position about their heading and their velocity to update their position. And we're going to use that now to deal with the robot, but we're going to have to use integration. So in this figure here, what we see is a view from above of the robot, and consider here its center of gravity, and imagine that there is a difference, a length between the left wheel and the right wheel. Our encoders are capable of indicating the velocity of the left wheel and the velocity of the right wheel. We want to be able to make an estimate of the velocity of the center. That can simply be done by averaging those two signals from the left and the right. But we also need to know at any given time the rate of rotation about some instantaneous center about which we might be turning. So if there's a difference between the velocity of the right wheel and the velocity of the left wheel, and those two wheels are not slipping against the ground, we can infer that there is a rotation about an instantaneous center, and that that rate of rotation is related to the difference between those velocities and the length of the baseline. With that little bit of processing now, we can go on to carry out integration. Integration of the angular orientation of the robot is indicated by integration of angular velocity over time. The X and Y positions update based on the velocity of the center and the orientation of the robot over time. The formulae for determining X position and Y position as an integral are given here. So now let's go ahead to a MATLAB session and see how this will proceed. The first thing we do is load the data from the encoders and set parameters like the length of the baseline and set initial positions or initial values for the states of the robot, its X and Y position and its theta. I'll take all those to be 0, consistent with the formulas on the slide, and then process those data to determine omega and velocity of the center. I'm going to run the code now. We'll begin to look at what is in the workspace. This generates our figure for our position over time. And what I want to show you is that in the workspace we get a velocity on the left. Those positions look like 0. So there's a time when the robot is just dwelling. It's just staying in one place initially and not moving, and then it starts to move. So we process those to get the velocity of the center and omega. Then we enter a loop in which for different time increments, now I just loop through an index, but these will correspond to time according to a variable that is also saved in the workspace called t. So I have stored those values at, that indicate how the time is changing, incrementing always forward, of course. So here, inside of the loop, I implement those formulae for determining angle and position using integration. And here I've used piecewise constant right endpoint for the procedure. We see that you take a sum of omega, leaving out the very first value, so we go from 2 to I, and multiplying by delta t. Similarly, for x and y, we take the sum of the velocity at the center. We have to take account of orientation, so we do dot times cosine so that we get element by element multiplication there, and also delta t here. So the weighting is 1 on all of the values from the beginning to the current time, except the weighting is 0 on the very first one because we don't use it. And finally, we plot x and y to see what our track is over time. Now, whenever we get results from a calculation like this, we want to be conscious of the ways that our procedures introduce error and create uncertainty in our inferences. And in this particular case, we find that dead reckoning is highly uncertain. If I made a small error in measuring v right or v left at any point, it would change the orientation of the robot, and the orientation of the robot in the early phases of this trip could have a disproportionately large influence on the final location of the robot as it proceeds. Because of that, dead reckoning is a procedure that always would be augmented with some other kind of localization. For example, pilots would have some waypoints or landmarks that they use along the way. For many years now, people also use radio aids to navigation, and these days people also would use something like GPS to get a second indication of their position over time, and then fuse together those different sources of data to come up with an overall estimate of position. So there are many different interesting examples of computational thinking motivated by this example, and one that I want to highlight is the idea of fusing multiple sources of information to gain a better understanding of the state of a system as it evolves. Thanks for your time.